here. And Australia is we're from Iceland, and Iceland is an island surrounded by ocean, just like Australia, and it's in many ways similar. Most of our towns and cities are lined around the coast, just like here. And in our central parts of Iceland, we have a big desert, just like here. Actually, in Iceland, we have the biggest desert in Europe, and we also have the largest glacier. And also in the central parts, we have volcanoes. And interestingly, you also have a big volcanic province in your northern and northwestern territories. So, and you'll learn about this a little bit today. I come from an island that is entirely volcanic, and sometimes we send postcards to our neighbors in the form of ash. And it's with love. And we are also not very good with money, so we own people, and when they ask us to pay them, we send them ash instead of cash. That's a little joke but it's all with love. But I'm a geologist. I work with geological mapping. I do a lot of mountaineering because I have to describe the rocks and draw maps. And this is my primary work, but I also get to monitor active volcanoes. And this is, for example, the volcano Holuhraun in 2014, a very large eruption. If you remember the volcano Eyjafjallajökull that nobody could pronounce, in 2010 I was also involved in researches on that volcano. And I get to see things like this, a lava fall, beside a waterfall. So it's quite different than most people get to see or used to see. But I run a photogrammetry lab where we fly airplanes or helicopters or drones, and we photograph geological formations, and we create 3D models. And I use this technology for my mapping, geological mapping. But I have also started to use it monitoring volcanic eruptions. And for example, our latest eruption in 2021, the Fagradalsfjall, I don't know if you've seen pictures of it or images. It was very popular, very accessible. It was nearby the capital, about 50 kilometers from the capital of Iceland, this little eruption. And I was flying over it regularly and taking images, creating 3D models, and monitoring the development of this volcanic eruption. And we were calculating the fusion rates, or how much magma was coming out of the craters, and passing this information to the authorities, to the civil protection. And this is, for example, one of the products of our work, is just to monitor. And this is the first time that a lava flow is monitored in so much detail. These are thickness maps, and you see that the center area, the red area, is about 120 meters that accumulated in 6 months. 120 meters of volcanics, of lava in the central areas of that lava field. So, but it's a very small eruption. And I was featured in this show here on Netflix, Earthstorm. There's a little chapter about my work there, which you can watch. There's a little bit of evolutionary theme, or not theme, but a little bit of evolution talk in this show that was not on the script when I saw it. And I was a little bit disappointed when I got to see the final product of this show. But the chapter about my work is pretty nice. But we are dealing with paradigms, and one of the paradigms that I deal a lot with is uniformitarianism and deep time. And I'm not going to go over these themes. And the other one is catastrophism, or the doctrine that changes in the Earth's crust have in the past been brought about suddenly by physical forces operating in ways that cannot be observed today. And so this is a paradigm that would be more aligned with biblical narrative. And so we're going to explore that from the lens of volcanism in the past. Now, I will use this word a lot, lava. And I suppose most of you know what a lava is, and you visualize lava as a hot, molten, semi-fluid rock, which it is. I mean, it's rock that is fluid and can flow and form rivers of lava. But lava, as it cools and solidifies and becomes rock, dark rock, we also call it lava. And that's confuses people. Many tourists come to Iceland and they hear about that Iceland is volcanic and there's lots of lava. And they walk there and for a week, and then as they leave, they say, "Where's all these lava people are talking about?" They were walking on it all the time. It was everywhere. It was just solidified. But I'm going to use the word lava for yes, also to describe fluid lava, but also to describe solidified lava. But lava has its origin, yes, or magma has its origins in the mantle or from partial melting of rocks in the crust. And it rises by buoyancy through the crust to the surface and then erupts as lava. And today we explain volcanic eruptions within the framework of plate tectonics. The Earth's crust is broken into plates, and it has at the boundaries weaknesses or fractures where lava can emerge and then intrude into the crust and then erupt at the surface. And I'll deal with plate tectonics a little bit in a session that I have here tomorrow. But one of the important things to do as a geologist is to compare and contrast. We have access to, well, in volcanology, we have access to volcanoes, to active volcanoes, and we can describe them properly, we can observe them, map them, and then with this data we can go into the past and compare it, this data that we just acquired from active volcanoes, and compare it with the past. And that's what we are going to do a little bit in this lecture. I'm going to try visually to show you comparisons and also contrast things that seem different in the past. So if I take, for example, this eruption here, Fagradalsfjall, which was a very, in Iceland we call them touristic eruptions because they are small and we can go and we can watch them. And this actually took place in a little valley, confined valley, so there was no real danger around this volcano. And people would just, going there was like going to a volcanic park. You know, we would just walk there around and see lavas erupting, and I would fly over. Yeah, there was some challenges, but yeah, it was a beautiful eruption. But it was very small. It formed lava with a volume of 0.15 cubic kilometers in 6 months. The total area it covered was about 4.8. Don't be intimidated by these numbers. We'll use them for comparison. The lava layers were relatively thin. They started as few decimeters, and then as the lavas flowed, they inflated to a few meters, 1 to 5 meters. And the effusion rate, which is the amount of magma erupting or lava erupting from the vent or from the crater, it's the flux. If you think about a river, the flow of a river was less than 10 cubic meters per second, and so we could observe lobes like this, developing and forming slowly and flowing. But it would be comparable to a little creek or a river like this, that a little bit bigger than this though, but in terms of flux and flow or effusion rates, this is what we can compare in terms of lava rivers, flowing out of the vents. Now in 74-89 we had a fissure eruption, and this is a fissure, or when lava comes from these long openings or cracks in the ground. And some of these fissures, there were about 9 episodes in this series of eruptions we call Krapla eruptions. And some of the fissures were up to 9 kilometers long. So it were pretty long fissures, but the eruptions were relatively small, 0.25 to 0.13 cubic kilometers in volume, and the areas were in between 6 to 24 square kilometers. But the effusion rate, the average effusion rate, was around 100 cubic meters per second, and peaks of around 300 cubic meters per second. And there's another eruption in 2014-15 called Holuhraun. It was about 6 months. It was an order of magnitude larger than Fagradalsfjall, volume of 1.2 square kilometers, no, cubic kilometers, area of about 84 square kilometers, and lobe thicknesses, or the thicknesses of the layer, between 5 and 15. And effusion rate comparable to Krapla, about 100 in average cubic meters per second, and peaks of 300. Now, this is an image of this eruption. You see how the lava flow extended through this landscape, covered the landscape, and it flowed about 18 kilometers. So it was a relatively long eruption and or long flow. And the eruption is very large in comparison to modern lava eruptions, one of the largest, in fact. And if you imagine a river as a comparison, but in the form of lava, this would be one example. This is a river in Iceland that has a flow rate of about 300 cubic meters per second. And the depth below that bridge is about 18 meters. So you imagine it's a relatively big river of lava that was flowing out of that crater and inundating that area. Now, as we go a little bit further back in time, there was an eruption in Iceland called Laki, 1783-84. That one was an order of magnitude larger than Holuhraun, which was very large. It lasted about 8 months. The volume was about 15 cubic kilometers. It covered an area of about 16 square kilometers. And I actually was going to do a little bit of, I was going to measure something here around so you could get more, get a better feeling of what a 1,600 square kilometers are. I don't know in terms of comparison with the city here of Gold Coast, what that would be. But it's a very large area. You drive here, and you see endless lava. It's endless. It's a very large area that was covered by this eruption. But note that the effusion rates were average 1,000 cubic meters per second, and peaks of 8,000. Peaks of 8,000. And that is, we are talking about very large rivers of lava flowing out of these fissures. And here you see actually two lava fields. One is the Laki 1783, which is the yellow one, and the Elgjá is from the 10th century. And that is the red one. These were comparable. These are lava fields that are of similar size and dimensions. And you see here Iceland. This is a 100-kilometer scale, and these two lava fields, the purple ones, in comparison to Iceland. So these were very large eruptions, and we have had a few of these in Iceland in the past. And the effects of this eruption, the Laki eruption, were humongous. A lot of pollution followed it in terms of SO2. There was, the rains became very acid because of the amount of sulfur dioxide that was emitted. And there was a lot of CO2 emission, about 304 megatons. And 1/5 of the population died actually by indirect effects of the eruption. A lot of grazing animals died, 50%, and that caused a famine. And so, and a lot of people got sick and or died from the famine and or other indirect effects of this eruption. And it is said that the pollution caused a cooling effect in northern Europe of about 1 degree. So the effects of this eruption were very dramatic. Okay, now we have gone through a spectrum of lava eruptions in the recent past. Now we are going deeper into the geological record, and we are going to now compare these eruptions, now that you have a little bit of a feeling of the dimensions of lava flows. And we are going to look at flood basalt provinces. Now the name there, flood basalt, gives you a hint of what we are going to deal with. Now these are very large eruptions. And surprisingly, we have provinces around all the globe with these types of flood basalts. In every continent we have them, even in Australia. And of course they are dated, different ages, and they are supposedly to have emerged at different periods. But what is a flood basalt? A very extensive lava flow of basaltic composition. So lava flows have, can vary in composition. Basaltic is a relatively primitive composition, which means that the lava is very fluid and can flow long distances. That has issued from a fissure, often to be found as part of a series of such flows, one on top of another, forming a plateau. You'll see pictures of this, but flood basalt volcanism of the past testify of volcanic eruptions of colossal scales in comparison to modern eruptions. So most of them were fissure eruptions like this one, like the Krapla fires, but on much larger scales. And let me just show you here. This is Iceland, and Iceland is about 100,000 square kilometers. It's 77 times smaller than Australia. But it's a relatively big island. And you see here Laki, 600 square kilometers. Now, these are lava flows that flowed in one of the smallest flood basalt provinces, and it's called the Columbia River Basalt in the US. Some of these lava flows, they are almost comparable in size to Iceland. They reach 76,000 square kilometers. The lavas flowed about 500 kilometers, 400 kilometers. And the volumes are over 1,000 cubic kilometers, each lava. And there are stacks of them. And so, some, the average lobe thickness is 20 to 30 meters, and some that inflated up to 100 meters thick. And the effusion rates, we are talking about averages in the range of 10,000 to up to 100,000, and sometimes up to 1 million. There's a little mistake there, but up to 1 million cubic meters per second. And that is really a deluge. And what's the Hebrew word for deluge? if I get points with Professor Davison. Yeah, but in lava terms, and we are seeing Amazon rivers of lava flowing out of these craters. And these provinces, as I mentioned, they are everywhere. In every continent we have them. Stacks of these types of lava. And even in Australia, Kalkarinji, they estimate that it's about over 500,000 square kilometers, up to 2 million, and individual flows within this province reached over 1,000 cubic kilometers. So we are talking about very large eruptions. In India, in the Paraná, I've done a little bit of work in the Paraná flood basalts. And in the Siberian traps, you have up to 7 million square kilometers covered by these gigantic lava flows. And as I mentioned, the Columbia River, which is one of the smallest ones, it has flows with volumes up to 4,000 cubic kilometers. Remember, Laki was 15. 15? Here we have lava flows up to 4,000 cubic kilometers. And this is accepted by, this is well documented in the literature. This is not something that we are making up. This is well documented and well known. It has been known for over 30 years, 40 years now, or more. But the implications of this are which I think we are exploring in more depth. But the conventional literature knows about flood basalts, and this is not our term. This is a conventional term that is used in the literature, flood basalt volcanism. But small lava streams like Fagradalsfjall, as they flow, they they will form little tongues or lava lobes. And as they cool and freeze, they are then covered by other streams. And if you would cut a cross-section through a lava field like that, a small one, you would see something that resembled what we see here at the top, little lobes. And let me use, I placed this computer here so I could use the mouse, and then I forgot. But here you see all these little lobes here. If you would cut a cross-section through a lava field of very small proportions or small scale, effusion rates maybe 1 to 10 cubic meters per second, it would look like this. But as they grow, the lobes, the lava flows, they also thicken and become more widespread. And when you get to flood basalts, you almost stop seeing these small lobes. They become very extensive, the lava flows. And an example here, and then they start stacking or forming piles of what we call tabular flows or simple flows. They look like just pancakes with plain parallel surfaces, contacts, because the effusion rates are so high that they just inundate the area and they just make things flat. They don't, no topography can stop it. It just fills the area and the surface and flattens the area. So you get stacks of flows that are very tabular and simple. In contrast to when you have smaller eruptions, low effusion rates, you would form something like this, much smaller units. Something like this. This is a wall of lava flows or a pile of lava flows in one of the shields in Iceland, and you see how chaotic it is, very small units and lobes of lava. But when you go into flood basalt provinces, then you start seeing things like the stacks of uniform, simple lava flows, and these are very thick, 20, 30, 40 meters thick lava flows. And you stop seeing those little lava lobes or small units. Well, here you have a sequence of lava flows that are smaller and thinner. So you find them also in flood basalts, but these are predominant, these very thick, extensive flows. And the Columbia, if you go to the Columbia River basalts, some of the flows traveled over 500 kilometers, and they reached very, thick flows. Many of them inflating because they had time to kind of flow all that distance, 500 kilometers. But in the Paraná flood basalts, here you see, for example, two flows, and this is a truck here for scale. And you see the thickness of the flow here, and then the flow on top was over 40 meters. This is in the Paraná in Brazil. This is one thick flow, and in a quarry. In Iceland, Iceland is actually quite interesting because it's in the middle of a spreading ridge, so that area has opened up, and then the large igneous province or flood basin province here of the Atlantic, called the North Atlantic Igneous Province, was split. So parts of it are here in Greenland, and parts of it are here in the UK or United Kingdom, in Ireland, and in the Faroe Islands. While parts of it, actually, the hotspot that created this volcanic province, we find it here, it continued active and formed actually parts of Iceland, or large parts of Iceland. But if we go to Greenland, you see this massive stratigraphy of these tabular flows. They're everywhere, and you see them. It's very clear, very visually obvious that, okay, we're not seeing small eruptions here. We are seeing massive eruptions that inundated the area and just flattened things out. And in the Faroe Islands, as I showed you before, this sequence of flows here, they are massive, very clearly, visually, it's visually effective and easy to grasp, right? It's easy to see that these are large flooding events and not small little catastrophic events. And we go even to Iceland, to the Miocene of Iceland, and we continue seeing this stratigraphy of flat flat tabular flows. And this is actually something I have written about and studied. If you want to read an article, I have it there. In the conventional literature, I described them, and I came to the conclusion that the effusion rates were around 100,000 cubic meters per second that formed these. It was large spills, just large spills, one after another one. And they comprise, a large proportion of the Icelandic stratigraphy, of the rock layers there. These are more of these simple flows, everywhere. And here a sequence of these simple flows, average about 11 meters to up to 20 meters thicknesses. And this is the type of stratigraphy or landscape that I map, that I work on, and I climb, and I have to document every single lava. I have to go through the pile and document the contact, and I'm constantly exposed to this stratigraphy, and I'm thinking, what is happening? Why is it like this? And then even if we go into other parts, older parts of the rock record, like even in the Precambrian, okay, this is interesting also for us, but we have fissures or these cracks which erupted lava, but they are eroded. We only see the cracks, and you see they are over 1,000 kilometers long. You see the scale there, 500 kilometers here. Now, what was happening? And then there's another, this is in Canada, Mackenzie Dike Swarm, and then we have the Lake Victoria, Africa. You see here the scale here, 100 kilometers. You see the fissures here. And this is Precambrian rock. So we'll discuss this a little bit, but and then I've been talking about effusive eruptions, the eruptions that flow, that erupt as lava flows and flow and cover landscapes. Now we also have another type of eruption which is explosive. This is for example, the Tonga eruption in 2021, and I learned that there are some people from Tonga here. That's very, yeah. I would want to hear your actually experience with this volcano when it erupted. But and I think the volume was around 10 cubic kilometers, so it would have a volcanic explosivity index of around 5 and 6. But if you go to the past, and this is Mount St. Helens, which was also had a volcanic explosivity index, I think around 4. And it's just here in comparison to other volcanoes explosive volcanoes that we have had in the past. Several orders of magnitude larger than Mount St. Helens. So even in terms of explosivity, the past is much more catastrophic. So the effects, imagine the effects of these large igneous provinces or flood basalt provinces on life, on the environment. You have thousands of square kilometers covered by lava, all the extreme heat, all the pollution. So, and imagine what is happening inside Earth. I mean, there's large turmoil. There's something big happening associated with these large volcanic eruptions. And there are possible, LIPS today, or large igneous provinces, are explained within the framework of plate tectonics, and I'll come to that in my session. But they seem to be associated with subduction slabs that accumulate here, that sank, and accumulated here at the core mantle boundary, and then they form these, what they call thermochemical piles, and they, by buoyancy, rose up again to the surface and erupted these massive flood basalts. But it's still debated how these flood basalts are really originated. And some even say they're associated with meteorite impacts, and it's also a possibility. But so of the entire crust, even the crust that we don't see at the surface, 95% is igneous or volcanic or related to magma, while 5% is sedimentary. But on the surface, about 25% is igneous and metamorphic. But of these 25%, a large percentage would be these flood basalt provinces that we see on the surface. about 25%. And if in the geological record, and you see here, this is just a simplified picture, but this is the youngest part of the rock record, and this is older, Permian. But in here we have all these large igneous provinces intercalated with sedimentary rock and other types of rock here. So, but if we look at the geological record, and almost every time you find a flood or find a volcanic province, it's flood basalts. If you go down the record, and almost every time you see that the record is flood basalt. Now, lava flow is kind of like the blood of the earth. When the earth gets a wound, it bleeds, and that blood closes the wound. So it's actually a pretty nice design if you think about these in terms of design. But if you get into a room and you see blood everywhere, now you think, wow, something dramatic happened, right? Something catastrophic. Hemorrhagic state is a medical term. No, and the same with Earth. Now we go there and we see in the rock record that almost everywhere in the sequence we get these flood basalts. What is happening? And as Dr. Leonard Brand will come into, when you look at the sedimentary rock in between, it also testifies of large-scale processes. So, what is happening? Then we come to time. Are these sequences really separated by millions of years? Because that is what the current paradigm teaches, that we have had these events are only episodic. They come and they happen. Yes, they are associated with mass extinctions today. So the people are kind of starting to see that these things are big, they have even global influence. They're even global events. But they are separated by long periods of time. And I'm not going to put much time in this. I don't know. Do I still have 11 minutes? Or? Yeah, but not put much time into this because this is work in progress. And I have a lot of observations on time in between because lava flows, they can be dated with radiometric datings. You can date every single lava flow. So you can test that age. So you can ask the question, do I see the time? Because it's not enough to just get a nice order. That order has to make sense if you want to apply some strict scientific criteria and be scientific. Every part of the puzzle has to fit. So, and often we get nice order, and people believe the order to be true. But do we see the time? And my experience now, mapping hundreds of lava flows, I mapped 100 for over 10 years, hundreds of lava flows in different provinces. And my experience is I don't see the time. And what was eye-opening, I went to Brazil once, and I saw a sequence of lava flows, and the uppermost lava flow had a weathered flow top, or the lava flows have a very defined internal structure, and the crust of it is porous. You see bubbles and vesicles, bubbles, and it's very vulnerable to weathering. And I saw that the uppermost lava flow was weathered into a nice soil, and it's very fertile soil. It's very good soil. But all the lava flows below it, they were perfectly preserved, Yet, there was you could even find the glassy rims of the lava flow, which is very also vulnerable to weathering. But all the lava flows below, they were perfectly preserved. And you see the sharp contact here between this flow here, this actually pink delineates the pink area, delineates the contact, and that is actually just hydrothermal alteration. It's not weathering. And when I started exploring the lava flows, different parts of it, I would always find perfectly preserved lava flows that were not weathered. Yet, radiometric ages, they place tens or even 100,000s of years in between each lava flow. And tens of thousands of years 100,000 years is a lot of time. There's a lot that happens in a time frame like this, especially in volcanic areas. I live in a volcanic country, and there's so much associated with that would disrupt the surfaces, or that can happen in this time. So the lava pipes lack evidence of prolonged time in between flows. For example, from my experience, lacks features of modern environments like erosion, weathering into the lava flow, soil formation, riverbeds. I don't even see like evidence of little creeks, riverbeds, almost nowhere, which you would expect. Tree roots, I mean, we do find plant remains, which is interesting. You find sometimes tree molds in the lava flows after trees, big trees, even in Iceland, that is, devoid of trees today. But I never see in the sediments, in some often in between lava flows, there are red sediments that have been interpreted as being soils, but they are not weathering into the lava itself. It's just sitting on top of the lava is perfectly preserved. And as I take a close look at these soil sediments, they're all volcanic. It's ash, and which makes sense. Of course, when you have volcanic eruptions, you have also ash deposits that are just deposited on top of the lava flows. So the stacks of flows, and I'll come back to this in a little while, but stacks of flows with same morphology, that's very interesting, because we see evidence of rapid deposition of the lavas. Sediments are volcanic in between flows, ash. They are synchronous, they're formed actually with the volcanic eruptions or shortly after. And plant remains are allochthonous, actually. I see a lot of evidence of that the plant remains were deposited or transported into place. They came from somewhere else, they were not growing in place. So this is just preliminary, and at some point I want to publish on this. But one thing on time is, for example, I find sequences of lava with exact same morphology. And what I mean, you see here that there are these red layers here in between the lava flows, these red layers. And this is actually braccia. It's as the lava flow, sometimes it brachiates. The sharing of the crust that is cooling, it slows the crust down, and as the fast flow moves, it kind of tears that crust up and it brachiates. And these flows are like this. Every single flow has braccia, and braccia is actually porous and vesicular and glassy, and it's very vulnerable to weathering. But we have a sequence of over 30 flows, and they are just copy-paste. They all look the same. They have exact same composition. They're copy-paste, one after another one. All look the same. And there are even some red beds in between some of these, just lying on top of the braccia, which again shows that these red beds have been interpreted as being soils. They are just ash deposits that are just deposited on top. But radiometric ages, they put a few thousand years in between these flows. And what kind of process has this memory, right? You form a lava flow, a type of a lava flow, then after a few thousand years, you form the exact same type of lava flow. Then after a few thousand years, you form the exact same type of lava flow again and again. Because so much can happen in a volcanic environment. I mean, Iceland is interpreted to be continuously opening, so there would be crustal changes, there are compositional changes, so you'd expect a variety of different types of morphologies, even within the volcanics. But we see these sequences, and again and again, and there are different sequences as well that I see there, that all of them have the same type of morphology. And to me, they are just telling me, I mean, this is part of the same event, not separated by thousands of years. So there are several observations like this that we are making on this stratigraphy, but they are challenging the conventional view that these ages can be trusted and there are absolute ages. So the relative ages are contradicting the absolute ages, and that's why I trust rather the relative ages than because there are several assumptions tied to the absolute ages or from the radiometric datings that can be challenged. So we are seeing a paradigm shift in terms of scale of geological processes, which is accepted, and partly accepted. And I'm not going to spend much time, but people are seeing this in the sedimentary record. As Professor Derek Agger wrote, there is no doubt that catastrophism, which was still a laughing matter not very long ago, has returned to the geological theory. More and more books and papers are being written about the rare event and sudden, often violent happenings. This is true in every field of geology, from extraterrestrial impacts to continental collision, and from storm deposit to episodic evolution. So this is an evolutionist just writing about his experience with the sedimentary record. And that's interesting to me because I was just focusing on the volcanics. But, as I mentioned, they separate the events by millions of years. In other words, the history of any one part of the Earth, like the life of a soldier, consists of a long period of boredom and short periods of terror. Now, what do I mean? But then you see also his motive. What do I mean by episodic sedimentation? Episodic was chosen carefully over other possible terms. Catastrophic has become popular recently because of its dramatic effects, but it should be purged from our vocabulary because it feeds the neo-catastrophist creation cause. I hope I have convinced you that the sedimentary record is largely a record of episodic events rather than being uniformly continuous. My message is that the episodicity is the rule, not the exception. And I would say that in terms of volcanics, large-scale volcanic eruptions are the rule rather than the exception. And what does that tell us? Where is science heading? And that's where I'm actually, in that question I'm more interested in than anything else. Where is it heading? Not where it has been. Because I agree with Leonard Brandt that we are seeing these shifts in paradigm. We went from the Great Cataclysm, and there was some data that supported it at the time. People didn't know much, but they connected it to the flood, biblical flood. But then there was some science, and we admit, we should be fair, that there was some science that led people to change paradigms, that they went towards multiple catastrophes, and they were still connecting it to the flood in some ways, but they were seeing evidence that seemed not to work well with that idea, and so they changed paradigms. Then there was more evidence, yes, there was more evidence that made people think about deep time and uniformitarianism. But I know there was also some, some things that were not right, they political at the time, that made people move towards that paradigm. But now we're seeing more science, and we are migrating back to the kind of neo-catastrophism. We are seeing large-scale events, even on global scale, are being taken in and associated with mass extinctions and large-scale events. So where is science heading? Can we say that we are going back to the traditional view? Or are we close to that? And that's what I find interesting. I think our next paradigm is going to be time. How do we understand geological time? And if we can understand them, then I think these events will be intercalated, will be associated, and will be then finally seen in their true nature. So just a quick speculations about where I put these lips. And you see that large part of many lips, actual large igneous provinces, flood provinces, they are in rocks that are devoid of life. So in terms, and that's a little bit tricky, because catastrophe, we use the word catastrophism, but if there's no life, there's no one to suffer, right? So why would it be catastrophic? We would rather use the term high energy events. They're high energy. And they could be associated with the creation event. Some of these very large eruptions of the Precambrian could be associated with the creation event. Some even say, well, when the life was without form and void, that there was a time period where there was tectonic processes. Maybe it relates to that, but creation event could be a good candidate. But then there are these large catastrophic, large lips that are associated with a rock record that has life. And we connect that with the flood. And even some of these, like in Iceland, they are kind of at the flood, post-flood interface. So some of them, probably some of these large eruptions continued as consequence, as the post-flood effects on crustal and crustal movements and so forth. This is just a so just wrapping up, catastrophism is back and now on steroids. Now, flood basalts bear clear evidence of catastrophic events on scales much greater than present. Large-scale catastrophes in the geological record are the rule rather than the exception. Flood basalts are the surface expression of great turmoil in the mantle in the past. That's important for geological models. Now, these events can be well accommodated into biblical models of origins, and I want to emphasize that understanding our catastrophic past is important for mitigating present natural disasters. There is a practical side to this. We're not just, being annoying. No, there is a practical side of this. If we understand our past, we can save lives. If we properly understand our past, we can save lives. And I think that's our duty as a Christian to focus on. So I thank you very much for your time, and hope to have lively conversations here afterwards.
So thank you very much, Dr. Oskarsson. What a terrific